everyone, welcome to the next session of Strength of Materials. We'll proceed to the next question on bars of varying cross section and how to calculate the stresses and strains in them. Let's read. A steel tie rod 50 mm in diameter and 2.5 meter long is subjected to a pull of 100 kN. To what length the rod should be bored centrally so that the total extension will increase by 15% under the same pull? The bore being 25 mm diameter, take value of Young's modulus as 200 giganewton per meter square. I'll start jotting down the data. As you can see, there is a steel tie rod 50 mm in diameter at the start and 2.5 meter long, which is subjected to a pull of 100 kN. So there is diameter 50 mm, length 2.5 meter, which is 2500 mm, and the pull, which means the load, is 100 into 10 raised to 3 Newton. To what length the rod should be bored centrally so that the total extension will increase by 15% under the same pull? The bore being 25 mm diameter, and the value of E is given as 200 giganewton per meter square, which is 2 into 10 raised to 5 Newton per mm square. Now if you read, okay, so there is some length of the rod which I need to find over here, up to which I am going to bore the tie rod centrally. So I will start. As you can observe, there are two cases. In the case 1, this is my rod. Length is L, as I have marked there. The diameter is D, which is 50 mm. The load is 100 kN. In this case, I can calculate delta L as PL by EA. Now, since the case is first case, so I'll write this as delta L1. The value of P is 100 into 10 raised to 3. Length is 2500. Value of E is 2 into 10 raised to 5. Area is going to be pi by 4, 50 square. Therefore, delta L1 will be obtained as 0.628 mm. This is the change in length if I consider that there is a solid bar and there is a load of 100 kN being applied on it. But this is not the entire problem. If you read, there is a particular length up to boring process is done and there is a bore made, and the change in length now will be 15% under the same pull. So for case 2, I'll have the same rod. There is a hole drilled inside. There is some load applied of 100 kN. This diameter, outside diameter, is 50 mm. Inner diameter, as you see, is 25 mm. The length in all is still 2500 mm. I want to find out the distance over here up to which the boring has been done. I hope the problem is now clear. For this case, the change in length, that is delta L2, I'll take for the case 2 as 2, that is delta L2 is 15% more of delta L1, correct? So that is 15% more, which means it is 15% of delta L1 plus obviously the value of delta L1. So I can say this is delta L1 plus 15 by 100 of delta L1, which becomes 1.15 times delta L1, which will be 1.15 into 0.628, which turns out to be 0.722 mm. This is the value of delta L2. Now, I need to calculate the value of x. For that, if you observe the figure carefully, there will be some amount of change in length in this portion plus change in length in this hollow portion. So I can say this is change in length in solid portion plus change in length in hollow portion will be equal to the total change in length. So I will write down delta L2 is elongation of solid portion plus elongation of hollow portion. For that, this value is 0.722. Elongation of solid portion will be PL by EA for solid plus PL by EA of hollow. This value of P is common, 100 into 10 raised to 3. The value of length for the solid portion is going to be, okay, now let's observe. If the value of L for hollow portion is x, the value for the solid portion will be 2500 minus x divided by value of E is 2 into 10 raised to 5. Area will be pi by 4, 50 square, plus here the value of P is 100 into 10 raised to 3. Length is x divided by 2 into 10 raised to 5 into, for calculating area, it is pi by 4 outer diameter square minus inner diameter square. 0.722 obviously to the left. If you observe, the only unknown is x. When I substitute in my calculator, I'll get the value of x as 1004.5 mm, or I can say it is equal to 1.0045 meter. This is the value of x. Obviously, this is also the value of x, so you can use any one of the two. Now let's take up another problem. A brass bar having cross-sectional area of 1000 mm square is subjected to axial forces shown in the figure below. As you can see this figure, this is a brass bar. There are load at various junctions A, B, C, D. Find the total elongation of the bar. Modulus of elasticity of brass is given as 100 giganewton per meter square. So I'll just convert quickly. E is 100 giganewton per meter square, which is 1 into 10 raised to 5 Newton per mm square. I hope now you'll be able to convert this. Now let's start solving. I have to find delta L, that is the total elongation of the bar. First, I need to find out the FBD over here. If you observe, this is a type 2 problem where the loading is going to be different at various junctions. So let's start with drawing the FBD. I'll start with the end portion AB first. This is AB. The length is 600 mm. I'm going to take everything in mm. To the left, I see the load is 50 kilonewton. Obviously, to the right, it has to be 50 kilonewton. I will just check once, and the direction obviously has to be tensile. If you recollect the derivation that I have made, we'll still do it again. 80 kilonewton at junction B is of pull type, so this will be positive 80. If I place 20 from here to here and I want to see the effect, 20 will cause a compressive effect, so I'll write minus 20, and 10 placed over here will also create a compressive effect. Total value is 50 kilonewton. 80 minus 20, 60, minus 10, 50. So this is how I draw the FBD of AB. Next, I'll draw the FBD of CD, because I know at one end the value is 10 kilonewton. One end the value of load is 10 kilonewton. This is of compressive type. So I know that from this end obviously there will be a compressive type of load. Let's just check once. 20 kilonewton is the first load at junction C, which is of pull type. so I'll write plus 20. 80 when placed here will press the end C, so it is minus 80, and 50 when placed here will again pull the bar, so it is going to be plus 50. If you observe, this value is minus 80 and this is plus 70, which is 10 kilonewton with a negative sign. I am not showing negative sign, instead I am drawing the arrow of compressive type, so I'll just write down the value is 10 kilonewton. Now I'll draw the FBD of B to C portion. The length is 1000 mm. Now this is little important and little different. I'll stand in between B and C and I'll first look to the left of B. When I look to the left, I will first observe 50 kilonewton. When I place this 50 kilonewton at B, it will cause a tensile kind of effect. So the load is plus 50. And if you observe 80 kilonewton, if you just take up the arrow and place it from this end, you will see that it is causing a compressive type of effect. So I have plus 50 minus 80. This value is minus 30, which means this is of compressive type. This is the value. Let's check from the right hand side as well. I stand in between B and C and I look to the right. First I'll take up 20. Suppose 20, if I pick it up and place it at C, I'll observe that 20 is causing a compressive type of effect. Similarly, when I place 10 kilonewton over here, I again see a compressive type of effect. So I have minus 20 minus 10, which makes it 30 kilonewton, and I have shown the arrow of compressive type. So I am not marking the negative sign. Either you show the negative sign or you show the direction. So I have shown the direction over here. So this is how the FBD of each bar is supposed to be made. Now I'll start calculating delta L1, delta L2, delta L3, and the summation is going to be equal to delta L. Now the only thing which I need to observe is for the first bar, let the change in length be delta L1. It will be positive because it is of tensile type. For BC portion, if I assume it is delta L2, I have to take a negative sign. The reason is this is of compressive type. And for the third one, again I'll write minus L3, minus delta L3, because this is of compressive type. So let's solve it. Delta L is equal to delta L1 minus delta L2 minus delta L3. For the first one, it is PL upon EA. P will be P1 because it is different for each bar. Length is again different, so L1. E is common for all of them, and area is different for each of. Area is also same for all of them. So here I'll write down minus P2 L2 upon EA minus P3 L3 upon EA. Here P1 value is 50 into 10 raised to 3. The length was 600. E is 1 into 10 raised to 5 and area is 1000 for each bar. Minus the load for the second one is 30 into 10 raised to 3. Length is 1000. E value is 1 into 10 raised to 5 into 1000. Minus P3 value is 10 into 10 raised to 3. The length is 1200. Divide by 1 into 10 raised to 5 into 1000. You can also take up E and A common and you can solve. After substituting calci, I get the value of delta L as minus 0.12 mm. I have to interpret the negative sign 0.12 mm decrease. This is the elongation of the bar. Actually, it is not of increase, it is of decrease type. It is very important to mention the meaning of the negative sign because any distance or length cannot be negative. The negative sign indicates something. Here it indicates that the length is of decrease type. Let's take up another numerical now. A member LMNP is subjected to point loads as shown in the figure. You can see at L 50 kilonewton, at M there is a load P whose value I do not know, At N the load is 500 kilonewton and at P the value is 200 kilonewton. I have to calculate the force P necessary for equilibrium. So I need to calculate the value of P and I need to find total elongation of the bar. Value of E is again given 210 giganewton per meter square, which is 2.1 into 10 raised to 5 Newton per mm square. Now first I will start with writing to find. I need to find the value of P and I need to find delta L, which is total elongation of the bar. I'll use the formula summation of force along x-axis is equal to 0. I have taken any force going towards the right as positive and any force going towards the left direction as negative. This is D'Alembert's principle and this is my sign convention. Therefore, 50 goes towards the left, so I take minus, P going towards the right plus P, 500 going towards the left minus 500 and 200 going towards the right plus 200 is equal to 0. When I solve this, I get the value of P as 350 kilonewton. Now, having found this value of P, I need to draw the FBD of each bar. I'll start with LM first. To the left of LM is 50 kilonewton, so I directly write 50. Obviously, I know to the right also it is going to be tensile 50. Now for that, I'll start with P. P is 350 kilonewton. It is causing a pull effect on M, so this is plus 350. 500, when I place it over here, it will be causing a compressive type of effect, so minus 500, and 200 when placed here will cause a tensile kind of effect. So if you check, this becomes 550 minus 500, which is 50 kilonewton. The length is 1000 mm. Next, I'll go to the bar NP. To the right, I can see tensile 200 kilonewton. I know obviously to the left also it will be 200 kilonewton tensile. I will still check. 50 when placed at this junction N will be of tensile type. P will be of compressive type. And 500 already is of tensile type. So when you calculate this, you get the value as 200 kilonewton. So this is how I draw the FBD for NP portion. Next, I'll draw the FBD for MN portion. So this is my MN portion. The length is 1000 mm. Now here it is something ambiguous. I do not know what will be the direction of the arrows. So I'll start with the left hand side. When I stand at the center and I look to the left, first 50 kilonewton at M will cause a tensile kind of effect. 350 kilonewton, when I place the arrow like this, the arrow is pointing towards M and it is causing a compressive type of effect. So I can say it is plus 50 minus 350, which makes it minus 300 kilonewton, which is of compressive type. Now let's check to the right as well. First I can see 500. When I pick it up and place it at N, the arrow is pointing at N and I can see it is causing compressive effect. When I place this 200 over here, I will see that it is causing a tensile kind of effect. So I will have minus 500 plus 200, which is again minus 300, which means it is compressive type 300 kilonewton here. So this is the FBD for MN portion. Now, if you observe for L to M portion, I will have delta L1 as a change in length. It will be positive because this is of tensile type. N to P portion is say delta L3. It will also be positive because it is of tensile type. And for M to N portion, I will have delta L2, which will be negative because this is of compressive type. So when I have to calculate the change in length delta L, it will be delta L1 minus delta L2 plus delta L3. I can again substitute like the previous problem, P1 L1 upon E and A1. Here the area is different for all the materials, minus P2 L2 E A2 plus P3 L3 E A3. For first one, the value of P1 is 50 into 10 raised to 3, value of L is 1000, value of E is 1 into 10 raised to 5 for all, and area is 600, minus P2 value is 300 into 10 raised to 3, length is 1000, E is 1 into 10 raised to 5 and area is 2400, plus P3 value is 200 into 10 raised to 3, length is 600, E is 1 into 10 raised to 5 and area is 1200. Therefore, I get the value of delta L as 0.27 mm. This is a positive value that I obtained. So here I'll just write down that it is elongation or increase. So with this 3 problem, I end this session. I'll see you in the next session with more numericals on the same topic. I hope you have understood the lecture. If you have any doubts, write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. See you in the next session. Thank you.